Section 3.6 is Summary of Curve Sketching. In the previous section, it was a combo section, we saw how we can derive information about the function f if we have information about the derivatives of the function, first and second derivatives. And at the end of the section, we did a couple of examples how this information can be put together in order to sketch the graph of a function. In this section, we're going to do more graph sketching. And to start with, let's consider the following. Let's sketch the graph of the function 2x squared divided by x2 minus 1. Okay? So I'm going to start by finding the domain of this function. The domain of this function, which I'm going to be denoting it by d sub f, this is a rational function, so the domain is everywhere. I mean, this function is everywhere defined except where the denominator is 0. So that's everything except plus and minus 1, right? Correct? So these guys are candidates to be asymptotes for the function, right? Vertical asymptotes for the function. So let's study the limit as x approaches, let's say 1 first, of the function f of x, and f of x is 2x squared divided by x squared minus 1, right? All right. And as x approaches 1, I'm gonna get, again, I'm not supposed to write this. Let me write it in red just to remind you that we're not supposed to write these, but still I'm gonna write it in order to elaborate. I'm gonna have 2 over, this quotient becomes 2 over 0. Am I correct? 2 over 0. And this is equal to, infinity. Am I correct? It's going to be equal to infinity. Well, is it plus or minus infinity? Depending where where x is approaching 1, right? If x is approaching 1 from the left, let's say, so this means x is smaller than 1, right? X is smaller than 1. If x is smaller than 1, x squared minus 1, or x squared is going to be what? One more time. If x is approaching 1 from the left, which means x is smaller than 1, x squared is going to be also smaller than 1, right? Because x squared is an increasing function on the positive side of the x-axis. So x squared remains smaller than 1, and this guy is going to be negative because x squared is smaller than 1, and then x squared minus 1 is negative. So this guy is negative. So we're approaching 0, but from the left, right? From the left. And if you approach 0 from the left, this becomes a negative number, close to 0, but a negative. 2 divided by something negative is negative, right? So that whole thing approaches infinity, but negative infinity, right? Now, if x is approaching 1 from the right, so it's approaching 1 from the right, so x is approaching 1 while being bigger than 1, right? So x squared is going to approach also 1, but x squared now is going to be bigger than 1. And this whole thing downstairs approach 0 from the right, correct? It's approaching 0 from the right. And as such, 2 divided by a number that's positive divided by positive becomes positive, but we know that this is going to go to infinity at the end of the day, but positive infinity this time, right? Make sense? So as x approaches 1 from the right, the function is approaching plus infinity, and as x is approaching 1 from the left, the function is approaching minus infinity. So I know that x equals 1. So I know that x equals 1 is a vertical asymptote, but more than this, I know how the function can be graphed around its asymptote, right? So is a vertical asymptote. And to be more precise, let's have a small graph illustrating what we just had. So this is the asymptote x equals 1. What we just found is as x is approaching 1 from the left, the green part, the function is blowing down, is going to minus infinity, right? So let's have this graph in green. So I have this behavior, right? Let me have a better one. So the function is behaving this way. So as x is approaching 1 from the left, the function is blowing down, right? And as x is approaching 1 from the right, the function is blowing up, as we discovered, right? So we get this. All right. So I know this for sure up to this point. All right. Now I'm going to study the limit as the other candidate to become a vertical asymptote. So I'm going to study the limit as x approaches -1 of the function right? And what? So this is going to be the same as before. This is going to be the same as before. 2 divided by 0, which is going to be infinity. But again, I need to determine the sign plus or minus, right? Well, if x is approaching -1 from the left, if x is approaching -1 from the left, this time around x squared is bigger than 1, right? X squared is bigger than 1. And then this whole thing downstairs is a positive thing all along while x is approaching -1 from the left, correct? So that's going to be a positive number, very small but positive. And then positive divided by positive is positive, right? So you get plus infinity. And now if x is approaching -1 from the right, x squared now is bigger, I should say smaller than 1, right? If x is approaching -1 from the right, x squared is smaller than 1 because the squaring function is decreasing, right? When for inputs that are negative. So if you give me something bigger than -1, I'm gonna square it. I'm gonna get something smaller than the square of -1, which is 1. So that's gonna be negative this time. So this is gonna be negative. The same colors go together. And then positive divided by negative, that's negative, right? Makes sense? So same thing as before. X equals -1 is also a vertical asymptote. And we know more than that. So let's graph. How about we graph the function around its asymptote over here? So that's -1. And we know that we've studied then when x is approaching -1 from the left, the function is blowing up. So as the inputs are approaching -1 from the left, the function is blowing up. So we get this. And for the other one, as x is approaching -1 from the right, the function is blowing down, right? So we get something like this. Correct? Let's now study the end behavior of the function. So let's study the limit as x approaches, let's start with infinity, plus infinity, of the function f of x. So f of x is 2x squared divided by x squared, and this whole thing, this quotient, behaves exactly as the leading term upstairs and the leading term downstairs, right? So that's going to be the same as this. Sorry, x squared downstairs. And this is limit as x goes to plus infinity of the function 2, which is 2, right? You agree with me? Leading term over leading term, right? So plus infinity forces the function to behave as such, and this is exactly 2, right? And as x approaches minus infinity, nothing changes. Same thing. So what can we infer? What can we infer up to this point? We can say that the function, we can say that the function has y equals 2 as a horizontal asymptote at both plus and minus infinity, correct? Okay, so keep this in mind. So all what we know is that I have this line y equals 2. That's the horizontal asymptote for the function. So I'm not sure where the function is at this point. Probably it's here, here. I have no idea, right? Here, here. I have no idea. But the idea is y equals 2 is a horizontal asymptote. Okay, and maybe something else. Maybe it oscillates in a fashion that, you know, and the distance between 2 and the function decreases all the way to 0 eventually. Obviously, this is not going to happen because this is a rational function. I'm not expecting the function to oscillate that much, right? So it's going to be one of these things that I just erased, one of these guys, right? So one of these and one of these, technically. Okay. All right. All right, let's keep going. Let's now study f. Let's try to find the critical numbers and see where the function is increasing and decreasing. So let's start by finding f prime of x. The function here is a quotient between two polynomials. So I'm going to use the quotient rule, and if you use the quotient rule, I'm not going to do it. I'm going to just, all right, you know what? It's not that bad. So 2x squared over x2 minus 1. So I'm going to have the derivative of 2x squared is 4x, and downstairs is x2 minus 1, minus the derivative of x squared downstairs, x squared minus 1 downstairs, which is 2x, divided by the square of the denominator, which is x squared minus 1. Okay. 4x times x squared is 4x cubed. Minus 4x cubed is 0. So that remains, the whole thing remains minus x divided by x squared minus 1 squared. Okay. So this is how much it remains upstairs, and then the quotient becomes this. And what can we say then? Let's study the variations of f prime and deduce information on f. This is an easy thing. Downstairs is always positive, right? And upstairs, the only time it's 0 is when x is 0. Let me just highlight that the only critical numbers are going to be of type 2 here. Those are critical numbers that allow the function f prime to vanish. There are no points lost from the domain of f to the domain of f prime, correct? Domain of f and domain of f prime are the same. All right. So as such, the critical numbers are going to be the one which allow the function to be the function f prime to vanish. In this case, it's going to be only 0. So f prime, okay, small table of variations here. So the only guy is 0. That's the only critical number. And f prime, let's have a row for it. That's minus infinity, plus infinity. F prime is 0 here. Before that, so downstairs is positive all the time. Before that, so if a number is negative, plug it here, you get a positive output, right? So positive here, and when you replace x by positive number, that thing becomes negative. So f prime becomes negative when x is positive. So what can you say about f then? F is increasing from minus infinity to 0. It's decreasing after that point. So what can you say about 0 then? At 0, you're reaching a local maximum, yes? So at 0, we're reaching local maximum. And what's that number at 0? Well, f of 0 is 0. You see? It's 0 divided by negative 1, so it's 0. So it's 0. And this is a local maximum. Yes? Okay. So now let's understand the concavity of the function. So let's run the concavity test, and to do so I need f double prime of x. F double prime of x. So you differentiate f prime. It's still a quotient. Alright, I'm not gonna do this one. And you should get 12x squared plus 4 divided by x squared minus 1 cubed. Okay. This is what we should get. Okay, and we want to study where f double prime is positive, where it's negative, correct? So what can we say about the numerator? This numerator is at least 4 no matter what x is, right? So in particular, this is positive for all x. Yes, for all x. What I mean by this, for all x in the domain. And downstairs, this is power 3, so whatever the sign of x squared minus 1, it's going to force the whole thing to get that sign, right? So let me record this. So f double prime of x has the same sign as x2 minus 1. And x2 minus 1 is x minus 1 times x plus 1, right? So we just have some room here. So as we said, x2 minus 1 is x minus 1 times x plus 1. Make sense? Okay, so let's have a table of variations for f double prime just quickly. So if x, so the first row is for where x lives, the number line. So I have two numbers where this guy is 0, namely negative 1 and 1. Both of these numbers are not permissible for f prime. So I'm gonna denote this by double bar just to indicate to myself that these points are not good points for f double prime, neither for f, right? So f double prime at those points doesn't exist. And between those two, the function is going to be negative. The function f double prime is going to be negative, and elsewhere it's going to be positive. And that's going to force the function to concave upward here, concave downward here, and concave upward here, right? So it's gonna concave upward from minus infinity to minus 1 and 1 to infinity. And it's gonna concave downward between minus 1 and 1. Okay. And now the last part is the sketching part. We're gonna put all the information together to come up with the graph of the function. Okay, we have some information about the behavior of the function around its vertical asymptotes. We know the horizontal asymptote. We know where the function is increasing, decreasing. We know that at 0, 0, we're gonna have a horizontal tangent, and we know where the function is concaving upward and downward. So it suffices now to just put the information together and graph the function. Okay. All right. So this is the vertical axis. This is the horizontal axis. So as we said, at 0, 0, let me start with this. At 0, 0, I have a horizontal tangent. So I have a horizontal tangent here. Let me indicate it by this. I know that x equals -1 and x equals 1 are vertical asymptotes. So I know that x equals -1 and x equals 1 are vertical asymptotes. Okay. Now what do I know? I know that the function is, I know the behavior of the function around the vertical asymptotes. I know it's gonna be here and here around -1, and this green portion and this one around 1. So the function is gonna look like something like this here, something like this here, right? And something like this here, and something like this here. We know that. And we also know that x equals 2 is a horizontal asymptote. So this is y equals 2 is a horizontal asymptote. So y equals 2 is a horizontal asymptote. Okay. And now let's read it. So from -infinity to 0, so from -infinity to 0, the function is always increasing. The function is always increasing. But it's gonna increase while concaving up to its vertical asymptote -1. So it's gonna increase all the way from -infinity to -1, which is the vertical asymptote, right? While concaving upward. So it's gonna concave upward. And I know that at -infinity I have the function is having y equals 2 as a horizontal asymptote. So the function is gonna start here. It's gonna go like this, right? So the function is increasing while concaving upward from -infinity to its vertical asymptote x equals -1. And y equals 2 is a horizontal asymptote, which means the distance separating y equals 2 and the function is decreasing all the way to 0. So this is gonna hug that horizontal axis or horizontal line eventually, right? It will never touch it, but it will get as close as one wishes. Okay. Next, we're still less than 0, so we haven't reached 0 yet. At -1, from -1 to 0 now, it's gonna keep increasing. It's gonna keep increasing. We know from -1 on this side, it's gonna start here, right? It's gonna keep increasing while concaving downward this time all the way to 1, to its second horizontal second vertical asymptote. It's gonna concave down, but between 0 and 1, it's gonna decrease, right? Between 0 and 1, the function is decreasing. So the function is gonna increase from -1 to 0 while concaving downward. It's gonna keep concaving, it's gonna keep being concave downward from 0 to 1, but now it's gonna decrease, right? And don't forget, at 0, 0, I have a horizontal tangent. So the function is gonna increase here, concave downward. It's gonna reach its horizontal tangent. It's gonna keep Oops. Okay, so it's gonna reach this point. This is the increasing part, and then it's gonna start decreasing while still being concave downward all the way to here, right? Makes sense? Okay, and I have a horizontal tangent here at 0, 0. And finally, from 1 to infinity, it's gonna concave upward while being decreasing. It's gonna concave upward while being decreasing. And don't forget, at plus infinity, the function has a horizontal asymptote. So it's gonna decrease but concave upward, so something like this. Okay. And finally, before we move on, let me just highlight one fact. You see this function 2x squared over x squared minus 1? If we observed from the get-go that this function is an even function, what's an even function? Means that f of negative x is equal to f of x, right? And those the geometrical characteristic of even functions are functions which are symmetric with respect to the y-axis, right? So one more time, if we realized at the beginning that the function is an even function, because look, if you plug in negative x, square the negative x here and square the negative x here, you're gonna still get f of x. So f of negative x is f of x. So the function is an even function. And as such, how does this translate geometrically? As we said, the function is gonna be symmetric. The graph is gonna be symmetric with respect to the y-axis, which means we could have done half of the work that we've done here and got everything, or the other half, for free in some sense, right? So we could have just graphed the function on one side of the x-axis, on one side of it, and reflect it in the y-axis and get the other for free. Okay, I intentionally did this just for you to be able to see how, you know, these things are intertwined, the whole thing. But if you want to do it in an economical way, the observation is worth it, right? I mean, just realize that f is an even function and just do half of the work. Okay. Moving on. The function that we dealt with in example 1 had two vertical asymptotes and one horizontal asymptote. But there are functions which have what's called slant asymptote or oblique asymptote that's neither vertical nor horizontal. Okay. Let me formally define this for you. So the line y equals mx plus b is said to be a slant asymptote or oblique asymptote of the curve y equals x, f of x, provided this happens. And let's explain what this thing is. So the line now is oblique. It's a slanted one. It's neither horizontal nor vertical. Okay, but the idea remains the same. The distance, I mean, it's still an end behavior thing, right? It's still an end behavior characteristic. So the distance separating the function from that oblique line, y equals mx plus b in this case, the distance becomes smaller and smaller eventually, right? Around plus or minus infinity. So one more time. The distance separating f of x and mx plus b, the distance separating f of x and mx plus b, so the y values of the function and the y values of the point on the line, right? So the distance separating the two becomes smaller and smaller as x goes to either the far right or far left, right? As x goes to either plus infinity or minus infinity. Makes sense? So that distance is represented in purple here, right? So this distance becomes smaller and smaller to 0 as x goes to plus infinity in this case, but that definition also takes care of the other end behavior, the minus infinity. Okay. All right. So here's a proposition. When does something like this exist? Well, for um, for rational functions, we know exactly when this exists. It exists precisely when the numerator is of degree 1 more than the degree of the denominator. This is what this proposition is saying. Okay, so for rational functions, p of x over q of x, p of x is a polynomial, q of x is a polynomial. This function has a slant asymptote if and only if the degree upstairs minus the degree downstairs is 1. And that is to say the degree upstairs is 1 more than the degree downstairs. Okay. So the natural question is, how can we find a slant asymptote? Well, one way to do it is by long division, and let me show you how. Let's consider the following example. Sketch the graph of f of x equals x cubed over x squared minus 1. Okay, so what's the domain of this function? What's the domain of this function? It's all real numbers except 1 and -1, right? Like before. Let's study the limit. I mean, how the function behaves around those vertical asymptotes. So very much the same as before. What you're gonna find is, I'm not gonna do all the details. I'm gonna just let you know what you would find. Well, if you're approaching -1 from the left, so this is gonna be infinity for sure, right? But the question is it minus or plus infinity? If you approach -1 from the left, you're gonna get minus infinity. And if you approach -1 from the right, you're gonna get plus infinity. Okay, so the function has -1 as vertical asymptote, and we know how the function looks around that, right? We just talked about it. So if this is the line -1, then the function is going to be, for the green part, it's going to be here, and for the blue part, it's going to be here, right? Okay, and for 1, we're going to still get the infinity, and for 1 from the left, what we're going to get is, so 1 from the left, we're going to get minus infinity, and 1 from the right, we're going to get plus infinity. Okay, so which means if this is the line x equals 1, for the pink part we're going to get this, and for the blue part we're going to get this, right? Okay, by the way, let me say something here from the get-go instead of just saying it at the end like I did in example 1. What we can make the following observation: this function is an odd function, because if you plug in a negative x, you get minus x cubed divided by x squared minus 1, which is minus f of x. So f is an odd function, and as such, the function is symmetric with respect to the origin. Okay, so the function is going to be symmetric with respect to the origin, and by this you can just do half of the work and get all of it, okay, and get the other half for free. That's what I mean. Okay, I'm still gonna do all of the work just for you to be able to see the entire story, but if you want, I mean, I would encourage you to actually do it on your own by just cutting the work in half. Okay. Now, so we studied the limit around -1 and 1, so we know that around 1 and the lines x equals 1 and x equals -1 are vertical asymptotes. Let me just write this too. So is it vertical asymptote, right? We know that. Now we're gonna study the end behavior. If you try to study the end behavior at plus or minus infinity of f of x, check f of x. It's a rational function, so it's going to behave as the leading coefficient, leading term upstairs divided by the leading term downstairs. So this whole thing is going to behave as x, right? X cubed over x, which is x. And this is plus or minus infinity depending on what you have here. So this is not telling us a lot, but you can sense that the function may have a line that controls it. Right, the function is still, let me be clear here. So for the plus, you're gonna have a plus infinity, and for the minus, right? For the minus, you're gonna get a minus infinity. Why? Because look, if x goes to minus infinity, that term is also going to minus infinity. And if x goes to plus infinity, that term is still going to plus infinity, right? So I know that the function is blowing up here and is blowing down here, but maybe it's blowing up and blowing down in a controlled way. And what do I mean by controlled way? Via like a line controlling that. And here, if you observe this, the degree upstairs is 1 more than the degree downstairs. And based on the discussion we just had over here, we are sure, because it's an if and only if statement, that a slant asymptote or an oblique asymptote is going to exist here. And how do we find it? We do a long division between x cubed, between the numerator and the denominator. We divide x cubed by x squared minus 1. So by the proposition above, by the previous proposition, right, we know that f of x has a vertical an oblique asymptote. An oblique asymptote as x goes to plus and minus infinity, correct? Now let's find that asymptote. Let us find it. All right, how do we find this? As we said, long division. I'm gonna divide x cubed by x squared minus 1. Okay. All right, so what should I multiply x squared with to get x cubed? X. Once you do so, you get x cubed minus x. And then you subtract the second polynomial, the bottom polynomial from the top, and as such you get x here, right? X cubed minus x cubed is x, and 0 plus or 0 minus the minus x is x, correct? Just to be more precise, how about we put this x underneath this? So what can you say then? X cubed, so x cubed is equal to x times x squared minus 1 plus the remainder x. Am I correct? By the way, this is a remainder. We cannot do anything anymore because we dropped below the degree of the denominator of the divisor, right? So if you remember from earlier course, college algebra, say, there was something called division algorithm, right? The remainder of the division between two polynomials has to be of degree smaller than the divisor, okay? And degree 1 is certainly smaller than degree 2. Anyway, so we get this, and then the function, what's the function here? What's the function here? It's x cubed divided by x squared minus 2, right? So x cubed divided by x squared minus 1 is equal to the quotient x plus x over x2 minus 1. So what did I do here? I just multiplied by 1 over x squared minus 1 both sides, or divide by x squared minus 1 both sides. You get this. And that guy is f of x. Agree? This guy is f of x. So f of x is equal to this. Now look now what happens. So what can you say about f of x minus x? Well, f of x minus x, I'm subtracting by x, right? So f of x minus this guy is equal to this guy. No? One more time. F of x minus this guy is equal to that guy. Yes? And then what can you say about the limit as x goes to plus or minus infinity of the function f of x? Well, sorry, f of x minus x. Well, this is the same thing as the limit as x goes to plus or minus infinity of x over x squared minus 1. Agree with me? Because f of x minus x, this difference is x divided by x squared minus 1. So I'm replacing this difference by this. And x, as x goes to plus or minus infinity, this whole thing goes to, okay, maybe one more step, because this is a rational function here. I can take just the leading terms, right? Okay, now let x goes to plus or minus infinity, and after you simplify by x, you get, so here you get 1 over x if you simplify by x, right? And then once you let x goes to infinity, you get that the limit is going to 0, right? So 1 over x goes to 0 as x becomes large in absolute value. So what did we show then? We showed that the limit as x goes to either plus or minus infinity, this difference is 0. And I hope that you see what I'm doing here. I'm trying to find the m and the b so that f of x minus mx plus b goes to 0 as x goes to plus or minus infinity. So in our case, m is 1 and b is 0, right? M is 1 and b is 0. Right? So that's the oblique line. Y equals x is a horizontal is an oblique asymptote for the function f. So this is what I can say now. So y equals x is a slant asymptote or oblique asymptote for the function f of x. Makes sense? Okay. All right, and we're going to proceed exactly as in the previous problem. We're going to find f prime. So we're going to find f prime to find where f is increasing, decreasing. So f prime of x. I'll let you do this. You should get x squared times x minus square root of 3 times x plus square root of 3. Let me know if you need any help to get to this answer. If you don't get it, divide by x squared minus 1 squared. Okay, and if you try to have a table of variations for f prime, and hence for f, to see where f is increasing and decreasing, look, the term, x squared divided by x squared minus 1 squared, all this guy is at least 0, right? is at least 0 for all x in the domain of the function. Yes? So technically just this product is what's going to force the sign of f prime. Okay. And what you get is, so this is where x lives, minus square root of 3 plus square root of 3. Okay. So here you're going to find positive between f prime is positive between minus infinity and minus square root of 3, negative between the two critical numbers, and positive afterwards. And hence f is going to increase here, decrease here, and increase here. Oh, I missed the zeros. Right. So what's going to happen here? That's f of negative square root of 3, right? So that value is going to be a local maximum. So this value is f of negative square root of 3. And if you do it, you should get minus 3 square root of 3 over 2. So this is a local maximum. And for f of 3, which is a local minimum, or f of square root of 3, which is a local minimum, you should get, as we said, it's an odd function, so you should get this. Okay. All right. So at this point, minus square root of 3 comma minus 3 square root of 3 over 2 and square root of 3 comma 3 square root of 3 over 2, at those two points I'm going to have horizontal tangent. And the function is increasing all the way to this point, decreasing all the way to that point, and then starts increasing again. Okay. Now to study concavity, I'm going to go to f double prime. And if you differentiate f prime again to get f double prime, and then simplify the expression, you should get 2 times x squared plus 3 times x minus 1 times x plus 1 times x. And the whole thing is divided by x squared minus 1 to power 4. Okay. And similar story as above, I want to find the variations of f double prime. And this guy here is always positive, right? This guy here is always positive for all x. Why? Because, I mean, 2 is positive, x squared plus 3 is at least 3. And this guy downstairs is for x different than negative 1 and x different than 1. This guy, whatever it is, you raise it to power 4, right? So hence this guy is positive. And what you get is this product, those 3 factors, the product of these 3 factors is gonna force the sign of f double prime. Okay, and if you analyze it, you're gonna get the following table of variations for f double prime. So for f double prime, what do we have? We have negative 1, 1, and 0. So we have negative 1, 1, and 0. So f double prime here, remember negative 1, the function f double prime and f are not defined at 1, at negative 1, right? And then at 0, f double prime is 0. And what you're going to find here is that f double prime is negative between when x is between minus infinity and negative 1. And it's positive between -1 and 0, and it's negative between 0 and 1, and it's positive after 1. So f, by the concavity test, f is concaving downward here, concaving upward here, and concaving downward here, and then concaving upward here, right? And how about inflection points? What are the inflection points in this case? 0 is certainly an inflection point. Why? Because the function changes sign there, and the function is continuous at 0, right? Remember, the function here is a rational function, so continuity and being well defined are synonymous. So at this point 0, f is continuous and it changes concavity. As such, this is an inflection point. So this is 0 as well, right? So 0, 0 is an inflection point. Remember, by definition, the inflection point is a point where the function changes concavity, but it must be continuous there, right? So 0, 0 is an inflection point, but -1 and 1 are not inflection points because the function, sure, it changes concavity, but the function is not continuous there, right? The function is not defined there in this case and in this case. So the only inflection point is just 0, 0. Okay. All right, so now we're ready to graph the function. As we said, the function is an odd function. It's symmetric with respect to the origin. Okay, let's graph a piece of it and reflect it in the origin. I've done the work for you. You just have to put them together. Let's do a piece of it and then deduce the rest. So we know that y equals x is a oblique asymptote, right? So let's say this is the line, y equals x. And we know that the line x equals -1 and x equals 1 are vertical asymptotes. Oops. Okay, something like this. Okay, let's go to the table of variations of f prime and see where the function has horizontal asymptotes. So f prime, this is f prime. It's 0 at 0, at square root of 3, and a negative square root of 3, right? So I'm gonna have 3 horizontal tangent at the point negative square root of 3 comma this number minus 3 square root of 3 over 2 and square root of 3 comma 3 square root of 3 over 2 and 0, 0, right? Because f prime is 0 at 0. And f of 0, if you remember, the function is x cubed divided by x squared minus 1. So if x is 0, the output is 0, right? So let's go to the graph and plot these points. So 0, 0 is here. I'm gonna have a horizontal tangent over there. Square root of 3 comma 3 square root of 3 over 2. So square root of 3 is bigger than 1, right? So something here. So the square root of 3 is something here. And 3 square root of 3 over 2, I mean, where is it? Is it below or above this line? Well, 3 square root of 3 over 2 since this number 3 over 2 is bigger than 1, I mean, a number bigger than 1 times square root of 3, this is bigger than square root of 3, right? Because you're multiplying it by a number bigger than 1, so it's going to exceed square root of 3. And since this line is y equals x, so this height here, this height is the same as square root of 3, correct? Because the y and the x match of any point on this line, the green line. So, so as such, we know that this height is bigger than this black thing, square root of 3. So it's going to be somewhere above, right? All right, so allow me to just erase all this mess here. Okay. So I'm going to get the horizontal tangent somewhere here. Okay. So this point is a local minimum, as we discovered, and the coordinates of this point are, as we said, square root of 3 comma 3 square root of 3 over 2. Correct? Okay. Okay. What else do we know? What else do we know? All right, so I think we're ready to graph then the graph. We said, okay, as I promised you, I'm gonna do half of it and reflect it with respect to the origin. I forgot to graph the function around the asymptote x equals 1. Let's bring this information down. So I know it's gonna be here and here, right? Okay. So I know the function is gonna be, let me choose an appropriate color. So I know the function is gonna be here, and it's gonna be here, right? Okay. Let's put the information together. So the function, I'm gonna just do it from 0 onward and then reflect it with respect to the origin, right? Because the function is an odd function. I mean, the whole information is here. If you don't want to reflect it, just embed all this information in the graph. Okay, I'm gonna embed half of it and reflect. Okay, so the same thing. The function from 0 is somewhere here, right? From 0 to square root of 3 is gonna be a decreasing function from 0 to square root of 3. But square root of 3 is bigger than 1, so it's gonna concave downward, right? So the function between 0 and square root of 3 is gonna decrease while being concaving downward. And it's gonna concave downward, it's gonna keep decreasing while concaving downward all the way to its vertical asymptote 1, x equals 1. So something like this then is gonna happen. Okay, so something like this is gonna happen. And then from 1 onward, concave upward all the way. Concaving upward all the way. But it's gonna keep decreasing from the 1 to square root of 3, right? To this number, this minimum, local minimum. Square root of 3 square root of 3 over 2. So it's gonna keep decreasing from 1 to this guy. So from 1 to this guy is gonna decrease while concaving upward this time, right? And then it's gonna continue concaving upward, but now it's gonna increase, and it's gonna start increasing, but around infinity. Remember, we have a vertical asymptote here, right? So we have not vertical, we have a oblique asymptote. We have an oblique asymptote here, right? Which is y equals x. So the function is gonna start increasing when it reaches the local minimum. So when it reaches this local minimum, it's gonna start increasing, and it's gonna go to its horizontal asymptote when x goes to plus infinity, right? So the function is blowing up, in a controlled fashion. All right. So you get horizontal behavior here and horizontal tangent, and then you're gonna get this, right? All right. All right, so for the second part, either you reflect in the origin or you go back to those two tables that we have and embed the information. I'm gonna do it on the cheap. I'm gonna just reflect in the origin. So this part is gonna be over here now, right? So here the graph crosses its horizontal tangent, and I'm gonna have a similar point to this, which is minus square root of 3 comma minus 3 square root of 3 over 2, right? This is the point we're talking about here, this point, right? So that point is gonna be somewhere here. Okay. So what are the coordinates of this point? Negative square root of 3 and negative 3 square root of 3 over 2. Okay. All right. And the graph is gonna be the symmetry of this with respect to the origin. So this is good enough, right? Okay, so this is and realize here that 0, 0 is an inflection point, right? I mean, it's in the picture because it was concaving up and then it starts concaving down, so it's an inflection point and the function is continuous there, right? Okay, so this is the end of this section.